In this video, you're going to learn how to determine the volume of a compound shape. In a similar fashion to areas, the volumes of shapes can be added together and the volume of a shape can be subtracted from the volume of another shape. So for example, let's consider the following shape, or the following compound shape. It's made up of a cone and a hemisphere. So I'll just sketch the shape. So what we have is a cone at the top and a hemisphere at the bottom. So we have a compound shape made up of a cone and a hemisphere. The volume of the compound shape is equal to the volume of the cone plus the volume of the hemisphere. So if the vertical height of the cone, so that's the center of the circular base, the vertical height of the cone is 28 centimeters, and the radius of this hemisphere, so from the center to any point on the surface, so I'll just show that from the center to any point on the surface, like that point, the radius is 7 centimeters, so 7 centimeters. We can determine the total volume of the compound shape. I just need you to realize that the circular base of the cone, so I'll just show the circular base. The circular base of the cone coincides with the top surface of the hemisphere. So the volume of the cone, as you know, the volume of a cone is given by the following formula: pi r squared h over 3, or 1 over 3 times pi r squared h. Now in this case, we know that the vertical height h is equal to 28 centimeters. H is known and r is also known, the radius of the circular base of the cone, which is 7 centimeters. Just in case you're struggling with that, this is a cone. It has a circular base. You locate the center of the base. The distance from this center to any point in the circumference of that circular base is the radius, which is 7 centimeters. But what we have here now is a hemisphere attached to this cone. The top surface of a hemisphere, or of this hemisphere anyway, is a circle. So it's this same circle that's the base of the cone now. That's also the top surface of the hemisphere. And the radius of the hemisphere from the center to any point on the surface of the hemisphere, or from the center to any point on the surface of the hemisphere, is also this 7 centimeters. So the volume of the cone is equal to what's pi? Approximately 22 over 7 times the radius squared, which is 7 squared times the vertical height, which is 28 centimeters, divided by 3, or times 1 over 3. 7 here, 1, that cancels this 2 here, because 7 squared over 7 is 7. So the volume of the cone is equal to, this can be evaluated using a calculator, and that gives 4,312 divided by 3 centimeter cubed. The volume of the hemisphere, or the volume of any hemisphere, is always equal to 2 over 3 pi r cubed. We know that the radius of this hemisphere is 7 centimeters, so the volume of this hemisphere is 2 over 3 times 22 over 7 times 7 cubed. And evaluating this using a calculator gives 2,156 divided by 3 centimeters cubed. Therefore, the total volume, the volume of the compound shape, so I'll call that V tot, is equal to the volume of the cone plus the volume of the hemisphere. This is equal to 2,156 centimeter cubed. In this example, we're going to determine the volume of the gap between two cylinders. So it has one cylinder of a certain height h, and it has a circular, base of radius. I'll call that big R. But imagine that there is another cylinder within this first cylinder. So imagine the first cylinder, this larger cylinder, is hollow, and you can fit another cylinder inside. So I'll just use dotted lines. So, I'll use a different color to show an outline of the other cylinder. This other cylinder has the same height as the larger one. Same height, so they have their bases coincide. And imagine a cylinder such that the radius of this circular top is small r. What's the volume of the region formed between the two cylinders? Well, the volume of that region, so the volume of the gap, is equal to the volume of the larger cylinder, which I'll call cylinder L, larger, minus the volume of the smaller cylinder. Now the volume of a cylinder, so is equal to pi radius squared times height. In this case, the volume of the larger cylinder is going to be equal to pi times uppercase R squared times the height, which is h here, and the volume of the smaller cylinder is going to be pi times lowercase r squared. So lowercase r represents the radius of the smaller cylinder times the same height, uppercase h. So the volume of the gap is equal to pi r squared h minus pi r squared h, because the cylinders have the same height. If I factorize and bring out pi h, I get this expression. So the volume of the gap is equal to pi h times r squared minus, uppercase r squared minus lowercase r squared. So if I tell you that the larger cylinder has a radius equal to 6 centimeters, and the smaller cylinder has a radius equal to 2 centimeters, the volume of the region formed between the two cylinders is equal to V gap. Pi is 22/7 times h, so I'll have to give you a value for h. Imagine the height of the cylinder is 10 centimeters. That's 10 times 10 into 6 squared minus 2 squared. So I'll just rewrite that neatly. So what we have is the volume of the gap is equal to 22/7 times 10, times 6 squared minus 2 squared. And that's equal to 22/7 times 10 times 36 minus 4, which is 22/7 times 10 times 32, which is equal to 7,040 divided by 7 centimeters cubed. It's approximately 1006 centimeters cubed. In this final example, we're going to determine the volume of a frustum of a cone. So here's a cone. And then here's another cone within the original cone. Just focus on this top bit. And one thing I'll let you know without proving is that the two cones are similar. So this larger cone and this smaller cone are similar. And the region formed when you subtract the smaller cone from the larger cone is this shape. So this shape here, which is known as the frustum of the cone. The volume of the frustum of the cone is equal to the volume of the larger cone minus the volume of the smaller cone. The volume of a cone is equal to 1/3 pi r squared h. So one way to determine the volume of the frustum of the cone is to determine the volume of the larger cone and subtract the volume of the smaller cone from the volume of the larger cone. But there's an easier method, and we're going to apply what we've learned about similar shapes. If you're given that the radius of the circular base of the larger cone, let's be in a different color, is 21 centimeters. So I'll just call this big R, and this radius is small r. So you can't see that. Small r, radius of this smaller cone, and big R, the radius of the larger cone. So if you're told that big R is 21 centimeters, small r is 14 centimeters, and that the vertical height of the large cone, so from the apex to the base, is, well, big H, and you're told that big H is equal to 35 centimeters. What's the volume of the frustum of the cone? Because the large cone and the small cone are similar, the volume of the large cone divided by the volume of the small cone is equal to a linear measurement of the large cone divided by a corresponding linear measurement of the small cone, all cubed. So we've done this when we looked at similar shapes in the previous video. What linear measurement do we have? The radius of the circular base. So the volume of the large cone divided by the volume of the small cone is equal to the radius of the large cone, which is big R, divided by the radius of the small cone, all cubed. So that's the same thing as this. Big R divided by small r, all cubed. We're given enough information to determine the volume of the large cone. We're given the radius of its circular base, and we're given its vertical height. So 21 centimeters for the radius of the circular base of the large cone, and vertical height of 35 centimeters. So the volume of the large cone, which is 1/3 pi r squared h, so uppercase R, uppercase H, volume of this cone is equal to 1/3 times 22/7 for pi times radius squared, which is 21 squared, times 35. And this volume is equal to 16,170 cm cubed. Now, to determine the volume of the small cone, instead of using this formula, which we can't actually use because we don't know the vertical height of the small cone, I can use this rule here. The volume of the large cone, which is 16,170 cm3, divided by the volume of the small cone, is equal to the radius of the large cone, which is 21 centimeters, divided by the radius of the small cone, which is 14 centimeters, all cubed. So radius of the small cone is 14 centimeters. So the volume of the large cone, that's what this is, divided by the volume of the small cone is equal to 21 over 14 all cubed. And that's equal to 21 cubed divided by 14 cubed, which is equal to 27 divided by 8. So this is something you can work out using a calculator. So we know that 16,170 divided by the volume of the small cone is 27 over 8. So cross multiplying will give that the volume, well, 27 times the volume of the small cone is equal to 8 times 16,170. So the volume of the small cone is 16,170 divided by 27. So the volume of the small cone is equal to 43,120 divided by 9 centimeters cubed. Therefore, the volume of the frustrum, which is the volume of the larger cone minus the volume of the smaller cone, is equal to 16,170 minus 43,120 divided by 9, which is approximately equal to 11,379 centimeters cubed.